So here we have problem 8.1, which is homework 4 of Mech 343. It is a cantilever bar and it is made of ductile material. It is statically loaded with Fx equal to 0, Fy equal to 175, and Fz equal to 100. We want to analyze the stress situation in rod AB by obtaining the following information. So the first part we have to do, A, is determine the precise location of the critical stress element. So we have to do part A. So the first thing we need to do is find the moments. So we can do the moment about the y-axis, and the one that, if you think about it, we'll rotate it around the y-axis will be Fz. So we have the moment about the y will be equal to, and it'll be going this way, so it'll be negative Fz, and then it will be 2 plus 6, so it'll be times 8. So that will equal negative 100 times 8, which will equal negative 800 pound inches. Then we need to do the moment about the z-axis. So obviously the Fy will be the what makes it rotate around the z-axis. So moment about the z will equal Fy, then also times 2 plus 6, so times 8. And Fy is 175 times 8. So that equals 1400. And then we can find there is no momentum about the z because of the direction of Fz. So then we can just find the resulting moment. And the resulting moment will be equal to the d squared and then the sum square rooted. So it'll be my squared plus mz squared square root, which equals 800 squared plus 1400 squared square root, which equals 1612.45. So we have the magnitude of it, so square that. Now we're going to find the direction of the moment, so it'll be theta, and the equation for that is inverse tangent of my over mz, and those will be the absolute value, so we have to make my absolute value. So inverse tangent of 800 over 1400, which is equal to 29.74 degrees. Now the last thing we need to do for part A is find the torque at point A, and that would be 175 my times 5, negative 175 times 5, which will equal negative 875 lbf per inch times it. So that completes all of part A, so we can check part A off. Now for part B, wants us to sketch the critical stress element and determine magnitudes and directions for all stresses acting on it. We can neglect the shear stress only if we can justify it. So part B, we want to find the magnitudes and directions for all the stresses. So we have the bending stress, sigma x, is always equal to 32 mr over pi d squared. We have those values, so that's 32 times mr, which is 1612.45, over pi. The diameter is just 1, so 1 cubed. That will be equal to 32 times 1612.45 divided by pi. 1644.24. 16,424.28, and that would be in PSI, which we can convert to 16.42 kPSI. So that is the bending stress, X. Now we need the torsional shear stress, which will be tau xz, and the equation for that will be negative 16t over pi d to the third. Oh, and I made a mistake. This is to the third. Pi d to the third. We have all those values, so it's negative 16 times t, which is negative 875, over pi 1 to the third. So we have 16 times 875 divided by pi. That equals 4456.34 psi, which is equal to 4.456 kpsi. So the last thing I want to do is the transverse stress, and it says it can be neglected if we can justify it, so we have to justify it if we're going to neglect it. So that would be tau, which for that would be 4v over 3a, which would be equal to 4, v being 175, and then 3, and then the a would go to pi over 4 times 1, the diameter, squared. So that would equal 4 times 175 divided by 3 times pi divided by 4 times 1, 297.1 psi. But so we can neglect it because it is so small. In comparison, it is small. So now we just need to sketch the critical stress element. So we have a square, and then our force is going this way. And you can think that this is x, and this would be z. So our sigma x, which is found, is 16.42 kpsi, and our tau xz is equal to 4.456 kpsi. So that solves all of B. So for part C, we want to, for the critical stress element, determine the principal stresses and maximum shear stress. So we have part C. We need to find the principal stress, which is just sigma 1, and the equation for that would be sigma x over 2 plus or minus the square root of sigma x over 2 squared plus tau xz squared. So we can plug in our values for that, and we get 16.42 over 2 plus or minus 16.42 over 2 squared plus 4.456 squared, which are obviously all the values pulled from here. We can do that. So 16.42 divided by 2 equals 8.21. Then we have the square root of 16.42 divided by 2 squared plus 4.456 squared, which is 9.34. So it'd be plus or minus 9.34. So therefore, sigma 1, sigma 2 will be equal to 8.21 plus 9.34 equals 17.55, and 8.21 minus 9.34 equals negative 1.13. So there are two values for our principal stresses. Now we want to find our max shear stress. And so tau max, the equation for that will be sigma x over 2 squared plus tau xz squared, all square rooted. Plug our values in for that, we get the square root of 16.42 over 2, all squared, plus 4.456 squared. When we solve that, 16.42 divided by 2 squared plus 4.456 squared, that gives us 9.34. And that will be in kpsi. So that solves all of the max shear stress. So therefore, we have done the principal stress and max shear stress. So we can check off part C, and we are finished with this problem.